Okay, welcome back. This is grade 10 physics. We're going to be talking about electricity. We want to particularly talk about those three terms on the screen there: current, voltage, and resistance. Just want to do a quick comparison before I start. If all you ever knew about nuclear power was accidents like Chernobyl and Fukushima in Japan, then you'd probably have a pretty bad opinion of nuclear power, of all things uranium, radiation, and basically nuclear physics in general. However, to give you a good analogy, if all you knew about electricity was the electric chair, you'd probably have a pretty similar opinion of electricity, and you'd probably think, wow, that's really, really dangerous. But when we use electricity, much like you're using it right now to watch this video on your phone, your laptop, in your house, electricity is contained in insulated ways, in wires and switches and so on, a bit like that one there. And it's obviously quite safe. So it can be dangerous, but we manage those risks and make it safe in a very, very safe way. And nuclear power is pretty much the same thing. Anything nuclear related, and I'm obviously not talking about bombs, we contain that radiation from the uranium and so on and those other elements that are radioactive and have it in a safe form and manage the risks, and we can use it quite easily. All right, so today we're going to have a quick look at electrical circuits. We want to understand how circuits move electrical energy, and we want to understand some current, voltage and resistance and what those terms actually mean. And we want to be able to define those terms by the end of this. All right, charges. So electrons, which have a nice little symbol like that one there, they have a negative charge, whereas protons have the positive charge. Okay. Now, when I talk about charges, I'm obviously not talking about cavalry charges. That one there is a picture of the Australian Light Horse at the Battle of Beersheba, which is considered one of the, it is the last great cavalry charge in history. It's a very interesting story if you want to look it up. But electrons, we say they're a charge carrier because they carry these negative charges. And we say that it has one negative charge as opposed to protons that has one positive charge. The positive and negative are things that we just made up. They're just terms that we came up with to describe that they're opposites. If we, at the start of doing all this work in physics, had have said that protons have a negative charge and electrons have a positive charge, there would be absolutely no difference in physics in our understanding of it. It's just a term we use to show that they're opposites. And the relative magnitude is the same. The size of that negative charge is the same as the size of the positive charge. They're just opposites. However, we can break this charge down, and charge is measured in coulombs. I'm not talking about that place up the Sunshine Coast of Queensland. Coulombs, it's named after a dead white guy who did a lot of research into this area, and its symbol is a capital C. We quantify a coulomb as the charge on quite a few electrons. That's how we've worked it out. We say that Q stands for charge, so that means charge on an electron, and the charge of an electron comes in these whole amounts of this elementary charge that we call one negative charge, or more correctly, it's 1.6 by 10 to the negative 19 coulombs, so it's quite a small amount. And in this way, charges are somewhat quantized, which means they come in these whole number amounts of that amount of 1.6 by 10 to the negative 19 coulombs, or one negative charge. We don't generally get anything smaller than that one negative charge unless we start talking about things like the Standard Model, and when we say that protons are broken up into quarks, we can have smaller than that amount of one charge. So electricity is just the flow of these electrons. All right, we tend to have fixed atoms, like in a metal. Metals are good at conducting electricity. Our atoms tend to be fixed in place, and the outer electrons, or the valence electrons, tend to be a little bit free to move around, much like in that diagram there. We don't generally talk about positive charge flowing. All right, we'll come back to that one later, but the positive charges come from the protons, and the protons are much, much bigger than the electrons. They're 1,800 times bigger than the electrons, so they tend to be fixed in place. The electrons, being 1,800 times smaller than every proton, are so much smaller and so much easier to move around, and hence we tend to have this sea of electrons, or which we refer to as the valence electrons, are free to move around the metal lattice, and hence that is what we move when we move electricity. We're moving those electrons around. And when we look at this, we have these three terms that we want to look at: voltage, current, and resistance. And that's what we'll look at. So voltage. Voltage is basically like the potential energy that pushes the electrons around the circuit. All right. So think of, in a gravitational field, an object can fall due to gravity. That height that it has gives it potential energy to fall. This is the same sort of thing. The battery or power source in a circuit gives it potential to move the electrons. That is the potential energy that causes the electrons to move, and that is the electricity that we use. The actual energy that we use is effectively just kinetic energy of the electrons moving, and it's caused by the voltage. So the voltage is just the push that pushes these electrons around. And don't forget, it's a form of potential energy. Sometimes we refer to it as EMF, or electromotive force, but this is the energy used up by every component in the circuit. Now, voltage is pretty simple. Again, named after a dead white guy. Its symbol is a capital V, and its units is volts, which is also a capital V, and it's the amount of energy per charge that we are moving around. Current, on the other hand, that's the amount of flowing electrons. How many electrons do I have flowing around a point at a particular part of the circuit? So think of it as the charge in a given period of time flowing past. So how many electrons per second are flowing past? And all the electrons in a direct current circuit that run around a simple circuit go out of the battery, around the circuit, through the components, and then back into the battery. And that is direct current, as opposed to the power in your walls in your home, which is alternating current, where the flow of electrons switches backwards and forwards. We do that when we want to transfer more power over longer distance. It's a bit easier doing an alternating current than direct current. So current, its symbol is I. It's measured in amps or amperes, again named after another dead white guy, and the symbol is a capital A, and this amps is just the charge per second that we're moving. Resistance, on the other hand, that's what slows down the electrons in the circuit. So usually this is the components of the circuit. So perhaps it might be in your kettle, the current or those moving electrons will flow through the wires, and then they'll go through the heating element in your kettle, and that's what slows them down, and we take the kinetic energy out of those electrons, and it becomes the heat energy of the actual coil. So anything that inhibits or resists the flow of the electrons, that's resistance. Sometimes we'll put resistors in a circuit to deliberately slow down the current, because there might be a particularly sensitive and expensive part of the circuit that we want to protect, so we put some resistors in there to slow the whole current down. Resistance is a capital R. It's measured in units called ohms. That is the unit of resistance, again named after a dead white guy, and the symbol for that one is omega. All right. Just a little bit more about resistors. All right, so sometimes resistors are drawn like this in a circuit. Sometimes we will draw a circuit and it'll just be a rectangle, a bit like that, but that's the same sort of thing. It's just these little guys here with the various colors to show there's a code there for how much actual resistance each one of those has. Sometimes we'll need to adjust resistance in a circuit, and that's a variable resistor. So there's a picture of one just there, but think of like a volume knob. As you turn the volume knob, you're changing the resistance in that part of the circuit because you're making the current go through a slightly thicker wire, which slows the current down, and the whole circuit will measure that change, and that's how we can change the volume of an amplifier or something like that. Things like a rheostat we commonly use in some of our high school experiments, because there's that little slider on the top there that we can move along, and we can manually adjust the resistance of a circuit to get a particular current or so on that we're after. All right, just a bit of an analogy. Think of a river, and we'll relate all these terms, current, voltage, and resistance, to a river. A river starts up in the mountains, and it will flow down to the ocean, okay? If both of those two diagrams show that. It is gravity that pulls that river down, or that water down from the mountain, and lets it flow down towards the ocean. The vertical distance that that water falls, like the height in the gravitational field that it falls, that's like its potential energy to fall. That's what the voltage is. That's effectively what the voltage does. It's a battery that causes that potential energy to make those electrons flow in the circuit. The actual water molecules, that's the current. So think of the physical water molecules flowing down that river as it makes its way all the way out to the ocean. Those water molecules are like a model of the actual electrons flowing in a circuit. The more water molecules flowing, the more current in the river. The more electrons flowing in a circuit, the higher the current. And the resistance is whatever slows down the flow of electrons. So any obstacle or anything that causes the water to slow down its speed is resistance. So let's look at some examples. This particular scenario here, you can see that that water has a long way to fall down that waterfall. So we would say that that is a high voltage in an electrical circuit. Think of the actual water drop from the mountains all the way down to the ocean. That is our voltage. The voltage will come from like the battery, like this thing here. The physical electrons will flow out the circuit at that smaller side of the little battery symbol there. The voltage is used to power this light bulb. The voltage, the energy, that potential energy is used there to become the light energy of that light bulb. But the connecting wires are just like these little bits of river where the water just flows and doesn't do a lot. Okay, we generally don't worry about the connecting wires because their resistance is insignificant compared to the major components in the circuit, so we don't really have to worry about it. Think of current as those water molecules again. This image on the left has a lot of water molecules flowing down that river, so you would call that a high current. Think of that as like a really, really big fat wire, like a big electricity overhead wire or something like that. Those big high tension power lines can carry lots of current. That's kind of like what that's modeling. Whereas a small little stream would be like a tiny little connecting wire or a tiny part of your circuit inside your phone or your laptop or something like that. Resistance, whatever slows the current down. You can see in all these images that the water's not flowing, the water current is not flowing. That's like a component in the circuit that's going to slow down the electrons and it's going to cause them to travel much, much slower. Even something like this one down the bottom here, this beaver dam, it's going to slow down the water quite a lot. That's like a really, really high resistance. In this little example here, you can see we've got a battery up the top there and we have electrons that will flow out that negative side of the battery. It's like there's a chemical reaction in the battery there that creates lots and lots of electrons on that side of the battery terminals, and hence they all will repel each other and want to flow around the circuit. And they'll all come around until they hit something that is a component of the circuit or something with more resistance. And that little yellow image there something gives you an idea of what's going on with these electrons, why there's more resistance. They've got to slow down for some reason. Maybe it's a choke point where they can't all get through as fast, for example, or perhaps in this example you can see where they might get repelled backwards or so on, depending on what the current is, and it's slowing them down as they go through there before they come out the other side there and head back around to the positive terminal of the battery, which they're obviously attracted to because they've got a negative charge. Just as a little sidebar, if you've ever seen that movie sort of mockumentary about Spinal Tap, there's a bit in that movie where they talk about how really cool their music is and how hard they play and so on, and everybody else's amplifiers and so on only go up to volume 10, but they're so good they go up to volume 11 because they're really, really funny. Incidentally, that's why the movie's rated on IMDb out of 11, where every other movie's rated at a 10. Anyway, enough of my terrible jokes. Let's have a quick break. If you want to have a break, pause the video and then come back. All right, welcome back. Let's have a quick look at this river and we'll do a quick bit of revision. Let's describe this in terms of volts and amps. Remember, volts is voltage, is like the vertical fall. Is there like a very powerful battery pushing that water down? In this particular section there, you can see it's relatively flat, so you'd say the voltage is quite low. Amps, on the other hand, is like the current. How many physical water molecules do we have in there? Obviously quite a lot because it's a very, very big, wide river. That's like a lot of electrons flowing down the circuit. Here's a waterfall. in 2 different seasons. You can see on the left-hand side there's lots of water going over. On the right-hand side, there's very little. So the left-hand side, in terms of amps, would be a high amperage. On the right-hand side, very low amps, because it's low current flowing. However, the voltage is the same in both of them because there is the same vertical fall. Let's have a look at this guy here. Obviously, a lot of water going over, so that's a lot of current, and a long way it's falling, so that's a very, very large voltage. Now we need to talk about this idea of voltage just a little bit more. In this little diagram here on the left, we have our battery here, where we have a current coming out through a load element that's there, and then the connecting wires going all the way back to the start. Now it's like that battery is increasing the potential from 0 up to some amount, and that's causing the potential energy for the electrons to flow. But then the potential energy of those electrons and the kinetic energy becomes, that energy is used somewhere. It's used in that load element to power something in this circuit, and that's where we see the drop back down to 0. So we often refer to as a potential difference between 2 points or a voltage drop in a circuit. It's because that energy, that potential energy of the battery, is used to power something in the actual circuit. Okay, if we look at these scenarios here, we have a little cell here. Incidentally, I've been referring to these things as batteries because we often call them that. But that little diagram there is an electrochemical cell. That's like one battery. Think of a AA battery or a AAA battery that you use at home. That's a single electrochemical cell. When we put multiple of them together, it becomes a battery. That's the actual term of the battery. It means multiple of the same thing put together. You know, in the army we talk about an artillery battery, like a gun battery. That is multiple artillery guns put together that all fire together. That's why it's called a battery. This is an electrochemical cell. When I put multiple ones together and I have multiple like this in my circuit, that's now a battery because I've got 3 electrochemical cells there. The smaller side is where the electrons come out and go around the circuit. So in the first example, we've got one cell, we've got one light there. All the energy of this circuit is used in that one little light, so it's going to have a very good current going through it. It's going to have a very good brightness. In the second one there, you now have 2 lights, so it's still the same voltage put into there, there's still the same energy going there, but you're going to split it amongst 2 different lights. They're going to have the same current because all the current that flows around this circuit this way is going to go through all of those lights and keep going, a bit like the river, all the way back to the start, but the actual energy is distributed between the 2. This one here on the bottom left is slightly different now because it's like the river is splitting into 2 bits. So think of the river splits into 2 parts and then comes back together. All the water molecules that split and go one way must go another way, must go either one arm of that river or the other, and they must all join back together. So the total current that comes to that battery will split between the 2 light bulbs and then join all back together at the other end there. And another way to draw that is that last diagram there. Right, electric current we measured using an ammeter, and because it's current, it's got to be in the actual circuit, in the series, to measure how many electrons are physically flowing through that circuit. So in this scenario here, we've got the little A in there to show that that's the ammeter and it's in the actual circuit there, measuring how many electrons are physically flowing through the circuit to go through that light bulb. Voltage, on the other hand, I've mentioned potential difference or voltage drop. We want to measure it in parallel. So this voltage meter is in parallel to my light bulb there because it's like we're measuring between this point here and this point over here. What is the potential difference or voltage drop across that light bulb? And we only care about the light bulb because the other bits just around the outside here are all just connecting wires and they don't really matter. All right, let's have a look here. So what are X and Y is the question here. All right, we know that the current's going to come out, the electrons will come out this way around our circuit, X is in that circuit and they continue to flow through X through the resistor there and back around to the top. So X is in the series of the circuit, everything must flow through there, so that must be an ammeter measuring current. Whereas Y is measuring between the 2 points either side of that, that resistor there, so that's measuring the voltage difference between before the resistor and after the resistor, so Y must be a voltage measuring a voltmeter. When we look at circuit current, all the current that comes out of the battery and goes into that resistor must keep going around the circuit and all the way back to the battery, so the current is the same before and after that resistor. So number 3 is our correct answer. Right, I've got a little question on the screen there that I want you to have a go at. And I want you to think a little bit about this question. Just pause the video if you like. You can read what the question actually asks. And basically, it's a question around why do we have to pay for electricity if current flows into the house and back out again? So the question actually is asking about where is the energy coming from that we're using? And this is a question that would have 3 marks allocated. Have a pause, have a think about that question and think more correctly about where those 3 marks will be allocated. And we'll come back in just a minute. This is your thinking time. Righto. So in this scenario here, all the energy that comes into a house gets used and all those electrons go back out. But it is the energy, the kinetic energy of those electrons that is caused by the power station. That's the energy that we're actually using and that's the energy you're paying for. Think about this question where there's 3 marks allocated and why there would be 3 marks allocated for this. There's a worksheet that goes with this particular question that you can have a look at that goes into a bit more detail. But essentially we want to discuss firstly that all the electrons coming into the house go back out of the house. That's true, but it is the energy of those electrons that we're using. It is that energy that's been used up by the components in our house, and that energy has to come from the original power station. There's your next mark. And that's the actual energy that we've got to pay for, not the actual electrons. How could you get a better result? Probably including a formula or something like that. We haven't actually discussed Ohm's law yet. That's in the next video. But you could bring in Ohm's law and explain how it all works using Ohm's law and the relationship between voltage, current, and resistance and what the actual energy is that we're using. That would get you your full 3 marks. Okay, that brings us to the end. Just have a think about this. Make sure you know what those terms are. Make sure you can define them. The next few slides have got a few other tasks for us to have a look at. This is an interesting video about a huge Van de Graaff generator in action, making those giant sparks. It's only a short video. You can have a quick look at him. This little video here is about something we used to have on batteries. Those little AA batteries there have that little little thing on the side there that you can see. That was a little voltmeter that they used to have to sort of test the strength of the battery. Have a look at that one. You can see how they look at a changing resistor inside a tiny little filament in there to actually create a little view of a charge sort of scale for you to look at. I've sent you some simulations from the textbook example CK12. If you haven't got those, pause the video. You can check out the names of those ones and look them up. The website's just CK12. If you Google it, you'll find it. So your task, make sure you've got an answer for the electricity board question that I discussed before that was worth 3 marks. Have a look at the simulations, check out the videos that are linked, and make sure you look at the next section before next time.